Welcome to Space Smarts, where we explore fascinating trivia, tips, and tricks from the cosmos. I'm your host, Neil deGrasse Tyson, and today we're diving into some mind-blowing facts about our universe. Get ready to have your mind blown as we unravel the mysteries of the cosmos, from the speed of light to the enigmatic Fermi paradox. Let's embark on this cosmic adventure together. So let's talk about speed, but not just any speed, the universe's ultimate speed limit, the speed of light. It's a concept that has fascinated scientists and dreamers alike for centuries. Now, we're used to things moving fast here on Earth, right? Cars, airplanes, even a cheetah sprinting across the savannah. These speeds are impressive, but they pale in comparison to the cosmic scale. But in the grand cosmic scheme of things, those speeds are practically snail-like. The universe operates on a whole different level of velocity. Light, my friends, travels at a staggering 299,792 kilometers per second. This speed is not just fast, it's mind-bendingly fast. That's roughly 7.5 times around the Earth in just 1 second. Imagine circling the globe multiple times in the blink of an eye. Now, this incredible speed has some mind-boggling implications for space travel. It sets a hard limit on how quickly we can traverse the cosmos. Think about it. The closest star to our sun, Proxima Centauri, is about 4.24 light-years away. Even at light speed, it would take over 4 years to reach it. That means the light we see from that star tonight actually left it over 4 years ago. We're essentially looking back in time. Now imagine trying to travel to a star system thousands or even millions of light-years away. The distances are almost incomprehensible. Even if we could travel at the speed of light, which is a whole other can of cosmic worms, it would take us thousands or millions of years to get there. The universe is just that vast. It really puts into perspective the vastness of our universe and the challenges of interstellar travel. The distances are daunting, to say the least. And it's not just about distance. The speed of light also affects how we communicate with spacecraft exploring our solar system. The delay can be significant. When we send commands to a rover on Mars, for example, it takes time for those signals to travel through space at the speed of light. This delay can be minutes long. Which means we have to be very precise in our instructions. Every second counts in space communication. So, the next time you flip on a light switch or gaze up at the stars, remember the incredible speed at which light travels. It's a marvel of the natural world. It's a fundamental constant in our universe, shaping our understanding of distance, time, and the very fabric of reality. The speed of light is truly the ultimate cosmic speed limit. Black holes, those enigmatic cosmic monsters that have captivated our imaginations for decades. But what are they, exactly? Essentially, a black hole is a region of space-time where gravity is so strong that nothing, not even light, can escape its clutches. Imagine this. You have a star, much more massive than our sun, nearing the end of its life. It's used up all its nuclear fuel, and can no longer support itself against its own immense gravity. So what happens? It collapses in on itself, squeezing all that stellar material into an incredibly small point called a singularity. Now here's where things get really weird. The gravitational pull around this singularity is so intense that it warps the fabric of space-time, creating a region from which there's no escape, a black hole. We can't actually see black holes directly because, well, they don't emit any light. But we can detect their presence by observing their effects on the surrounding matter. For example, if a black hole passes through a cloud of gas, it's like a cosmic vacuum cleaner, sucking in the gas and creating an accretion disk of superheated material that swirls around the black hole, emitting intense radiation that we can detect. And talk about recent discoveries. Astronomers have even managed to capture the first ever image of a black hole's shadow, a stunning achievement that further confirms Einstein's theory of general relativity. Black holes remain one of the most fascinating and mysterious objects in the universe, pushing the boundaries of our understanding of gravity, space, and time itself. Now let's ponder one of the most profound questions in all of science. Are we alone in the universe? This question has fascinated humanity for centuries, driving both scientific inquiry and imaginative speculation. The universe is unimaginably vast, containing billions upon billions of stars and likely even more planets. Each of these stars could potentially host planetary systems, some of which might harbor conditions suitable for life. So, statistically speaking, it seems incredibly improbable that we're the only intelligent life out there. The sheer numbers suggest that life should be abundant, yet we find ourselves in apparent solitude. and yet we haven't found any concrete evidence of extraterrestrial civilizations. Despite our best efforts, the cosmos remains eerily silent. No radio signals, no alien artifacts, no giant spaceships parked in our orbit, at least not that we know of. Our search has turned up nothing but cosmic background noise. This is the crux of the Fermi paradox, named after physicist Enrico Fermi, who famously posed the question, where is everybody? If life is so likely, why haven't we found any evidence of it? There are many possible solutions to this paradox, each more mind-boggling than the last. Some theories are grounded in science, while others venture into the realm of the speculative. Maybe intelligent life is incredibly rare, and we're one of the only civilizations to have ever arisen in the entire universe. This would make us an extraordinary exception in a mostly barren cosmos. Or perhaps there are other civilizations out there, but they're so advanced that they've transcended our current understanding of technology and exist in ways we can't even comprehend. They might be using forms of communication or travel that are beyond our detection capabilities. Some theories suggest that advanced civilizations might deliberately choose to remain hidden, observing us from afar, like cosmic anthropologists studying a primitive species. They could be waiting for us to reach a certain level of development before making contact. Or perhaps the distances between stars are simply too vast, and the time it would take to travel between them is so immense that interstellar communication or travel is practically impossible. The universe's scale might be the ultimate barrier. The Fermi paradox is a humbling reminder of our limited perspective and the vastness of the unknown. It forces us to confront the possibility that we might be missing something fundamental about the nature of life and the universe. It challenges us to think critically about our place in the cosmos, and to keep searching for answers to one of the most fundamental questions we can ask. Are we alone? The quest for understanding continues, driving us to explore further and look deeper into the mysteries of the universe. Now let's talk about a true scientific marvel, the Hubble Space Telescope. A telescope that has revolutionized our understanding of the universe and captured our imaginations with its stunning images of the cosmos. Launched in 1990, Hubble orbits high above Earth's atmosphere, which allows it to capture incredibly sharp images without the distortion caused by our planet's air. Think of it as having a giant, incredibly powerful telescope floating in space, constantly peering into the depths of the universe. Hubble has made countless groundbreaking discoveries, from helping us determine the age of the universe more accurately, to revealing the existence of supermassive black holes at the centers of galaxies. But perhaps its most profound contribution has been its ability to capture breathtaking images of celestial objects, images that have inspired generations of scientists and stargazers alike. Who can forget the iconic pillars of creation, towering columns of gas and dust where stars are born, or the Hubble Deep Field, an image that revealed thousands of galaxies in a tiny patch of sky previously thought to be empty. These images are more than just pretty pictures. They're windows into the vastness and beauty of the universe, reminding us of the wonders that lie beyond our own planet. Hubble has fundamentally changed our view of the cosmos, revealing a universe more awe-inspiring and mysterious than we ever imagined. It's a testament to human ingenuity and our insatiable curiosity to explore the unknown. Let's journey back to the very beginning, to the event that birthed our universe, the Big Bang. This monumental event set the stage for everything we know and see around us today. Now I know what you might be thinking. A big explosion that created everything? Sounds a bit far-fetched, right? But let's delve deeper into this fascinating concept. But hold on, because the Big Bang theory is supported by a wealth of scientific evidence. Scientists have spent decades studying the cosmos to piece together this incredible story. So, what does the theory actually say? What are the details that make this theory so compelling? It suggests that about 13.8 billion years ago, our entire universe was compressed into an incredibly hot, dense state. A singularity. This singularity contained all the energy and matter that would eventually form everything we see today. Then, for reasons we're still trying to fully understand, this singularity began to expand rapidly, cooling and stretching space itself. This expansion marked the birth of our universe. Think of it like inflating a balloon. The more you blow air into it, the larger it gets. As you blow air into it, the balloon expands, and the dots you might have drawn on its surface move farther apart. This is similar to how galaxies move apart as the universe expands. In a similar way, as the universe expanded, the energy within it cooled and condensed, eventually forming the building blocks of matter as we know it: quarks, protons, neutrons, and eventually, atoms. These atoms would go on to form everything in the universe. Over billions of years, gravity pulled these particles together, forming stars, galaxies, planets, and eventually life itself. The universe as we know it began to take shape. Now, how do we know any of this actually happened? What evidence do we have to support this grand theory? Well, there's a lot of evidence that supports the Big Bang theory. Scientists have gathered data from various sources to build a compelling case. One key piece is the cosmic microwave background radiation, a faint afterglow of the Big Bang that we can still detect today. This radiation is like a snapshot of the early universe. It's like the faint echo of the universe's birth, and it provides strong evidence for the Big Bang theory. This afterglow helps us understand the conditions of the early universe. The Big Bang theory is a testament to the power of scientific inquiry, our ability to piece together the history of the universe from billions of years ago. It's a remarkable achievement of human curiosity and intellect. It's a story that continues to unfold as we make new discoveries and refine our understanding of the cosmos. Each new piece of evidence brings us closer to understanding the true nature of our universe. Thanks for joining us on this cosmic journey. If you enjoyed these space smarts, don't forget to like, subscribe, and hit the bell icon for more fascinating facts about the universe. Remember, the universe is a vast and mysterious place, full of wonders waiting to be discovered. So keep exploring, keep questioning, and keep looking up. Until next time, keep those cosmic questions coming.